is a correction to that. That is precisely the Schwinger term. Well, the way to see that how it arises is to realize that application of the derivative and time ordering of operators do not commute. So you cannot just differentiate a time-ordered expression without producing extra terms. So this is because, well, how can we, well, what is T ordering? T ordering means that we arrange the operators such that the time flows from right to left. So if x0 is larger than y0, then we take the operators in the order they're written. But if it's negative, then we need to reverse the order. And now when we differentiate this, okay, derivatives, spatial derivatives acts only on phi, but the time derivative will also act on the theta function. And here we are missing these terms. So we need to accurately differentiate this expression. So we act by some differential operator on the whole expression, not just on the field. And so we need to pick up the terms that arise from differentiating the theta function. So let's do it explicitly. So what do we get? So we need only to look at the derivative in time. Well, then we apply the chain rule. And so this will be, so first of all, there will be a term where both derivatives act on the phi. Then there will be a term where one time derivative acts on the theta function and the other on the phi. And when we differentiate the step function, we get the delta function, right? So the derivative of the step function is the delta function. So what we get is delta of x0 minus y0. Yeah. That's a plus, so thank you. And then we will get phi dot of x, phi of y. And here you see that this is an inverse step function. So when we differentiate, we get the minus delta function. So here we get minus phi of y, phi of x. And there is a time derivative. So dot denotes the time derivative. And finally, there is a term where both derivatives act on the theta function. So this will produce delta prime of x0 minus y0. And here again, I will have phi of x, phi of y. Let's see. Minus phi of y, phi of x. So the interesting thing that what happened is that you see that what remains is a commutator. Yes?
I was wondering whether that
Which of the terms? This term? Well, this two derivatives x on phi. No, this is just the next derivative. So okay, so one thing that we observe is that phi dot is equal to the canonical momentum of phi, and what stands here in the brackets is the commutator of pi with phi, which is by canonical commutation relations is equal to the delta function. Now the last term is a little bit more tricky. Okay, so we can use the fact that pi of x, and now there is a another important point is that the delta function in front imposes the condition that these operators are taken at the same moment of time. So then we use the commutation relations, which tell us that this is equal to minus I delta of x minus y. And then in the second term, it seems that we get 0 because the field operators commute with themselves at equal moments of time. But one has to be more accurate because in front we have the delta function, the derivative of the delta function. So in fact, we should use the following equation. So if you have the derivative of the delta function of t multiplying some function of t, so this you can write as derivative delta times f of 0 plus t f prime of 0 plus something for the t squared. So in this term, and suppose that here we assume that f of 0 is 0, which is the case in the last term. So if you set time coordinates of the phi is equal, then they will commute. So we only keep the second term, so this will be equal to t delta prime of t f of 0. The other terms don't contribute. And the claim is that so when the delta function only really works when we integrate. And so here, when we integrate by parts, what we get is the derivative effects on t. So this will be minus delta of t f prime of 0. Yes?
Wait, this is under a derivative, so should we do something like integration with? So by integration by parts, you took the derivative off the delta.
Yes.
Shouldn't that also transfer it to the f?
It transferred to the f in the sense, right? So that appears with the derivative. The important point here is that, so this is a distribution in the sense that it only makes sense when you multiply it with some function and integrate.
Prime 0 is a constant, right?
Yes. So then, of course, when you integrate in that integral defining this distribution, if you integrate by parts, the derivative will act on f and on whatever you integrate with. But since f of 0 is 0, it only picks up the term that with the derivative of f. And so here the derivative again produces the canonical momentum. So the first term here combines into the Klein-Gordon operator and gives 0. So finally, the result of this computation is that the Schwinger term is equal to what? So it's equal to delta of x0 minus y0 times the commutator of phi of x with phi of y. So this is minus I delta of x minus y, right? So this is the delta function of the spatial coordinates with the minus I. And so what we get is the four-dimensional delta function. So all in all, we get the following equation for the propagator. From which we conclude that first of all it's a function of difference. So d. So far, if we would be not making any assumptions, we would could have thought that d is a function of x and y separately. So from this equation, we immediately see that it's a function of the difference. Then we need to solve this equation, and this can be done by Fourier transform. So we can substitute d of x as an integral d for pi divided by 2 pi to the 4 e to the minus I px. And then some Fourier image of the propagator. So what we get is an algebraic equation. So here we'll have minus p squared plus m squared d of p is equal to minus I. So we get that the Fourier image of the propagator is a simple algebraic function. So that's the most important formulas in quantum field theory. And so in principle, we need to substitute it back and do a Fourier transform. But now, doing this integral, we run into trouble because the integrand has poles on the domain in the domain of integration. And so what do we do with these poles? And well, the expression doesn't seem to be well defined. Well, the reason is that we could have expected something like that to appear, because you see that what we are doing here, we are solving a second-order differential equation without imposing any boundary conditions. And of course, that's impossible. So a second-order differential equation has solutions parameterized by two functions, right? So you need to impose two boundary conditions somewhere. Okay, so so this is reflected in the appearance of some singularities in the solution, and the way we remove the singularities will parameterize the requisite set of different boundary conditions. Yes.
Thanks. Sure about something that happened earlier. On the middle board, on the right, the top line, as you pointed out, D depends on the difference x minus y. In the line immediately below it, are you x minus y to x?
Yes, yes. So just to write a shorter formula. Anyway, so if you draw, well, say we want to do this integral over P0 first, okay? So then there will be two poles, which actually correspond to the on-shell condition. So these poles correspond to P0 equal to minus P spatial squared plus M squared. And P0 equal to plus the square root. Now, I don't really want to explain in detail how one should resolve the singularity. But the idea is that you just draw the contour that goes a little bit around this point. So so you go outside into the complex energy plane, and the integral then should go around the poles in this way. So if you encircle them in different way, you get different answer, of course. So in particular, if you encircle them both from the top, that would be, I forgot, either advanced or retarded Green's function. If you go from the contour goes from below the poles, then it will be advanced. And so the correct prescription for the Feynman propagator is this one. Why so? The reason is that you want the Green's functions to be well-defined functions of time. So they should behave well at plus and minus time infinity. And then you can see that this is the prescription that makes them well behaved at infinities. So in explaining this in detail will take us too far away. So, and this is explained in the notes and in the textbook. So in principle, you could read it there. So let me just state the result. So you need to encircle the poles in that way. And that's equivalent to adding a small epsilon here with the plus sign. So this is called epsilon prescription. And so a simple exercise is to show that it's equivalent to drawing this picture. which is I leave you as a home exercise. Okay, so so now we have everything to compute arbitrary green functions. We know how to do the weak contractions. The result is some product of propagators. Each propagator is given by this function. By the way, you can, of course, do the integration. It gives some special function that's called the Hankel function. Anyway, I will not do it because, as we will see later, this Fourier integral representation is physically much more important. And yes?
Would you mind why add it if so?
So if you don't add it, then the integral will be equal to infinity, right? Because when t squared is equal to m squared, you have pole on the axis of integration. So this epsilon prescription regularizes this infinity. So now the contour is shifted a little bit from the pole, and this defines the integral, makes the integral well defined.
Do you also need to add a limit to the integral, limit as epsilon approaches 0?
Sorry, to add what?
A limit in front of the integral?
Yeah, sure. It's assumed that this is infinitely small. Any other questions here? Well, then let's do some calculation that involves interactions. So let's do Feynman diagrams. But now in an interacting theory. So we, in the last lecture, we computed the 4-point Green's function in the free scalar theory. Now let's switch on interactions and compute the first correction to that. So let's compute the 4-point function. At order lambda to the 1. So for that, we have this formula that I'll not write it down again. You should have it in the notes, where in addition to the 4 fields that we insert to define the Green's function, we also have this exponential that we should expand. So this exponential contains the integral of the interaction Lagrangian. Okay, so at the leading order, when we expand the exponential to the first order in lambda, we will have just one interaction Lagrangian integrated over space. And here we'll have the Green's function. So we will have the fields that define the Green's function. And then we'll have phi to the 4. So at point x. So you can write it as phi of x, phi of x, phi of x, phi of x. And so again, everything reduced to the Green's function of 3 fields. But now instead of 4 fields, we need to compute the Green's functions of 8 fields. Okay, so this is an 8-point 3-field Green's function. So what we should do is we should again apply the Wick's theorem, which will give us all possible contractions. And if you count how many you have, it's well, I counted 105. So combinatorics here gives 105 terms, which would be too much to cover in one lecture. But fortunately, many of these terms are just the same. Because you see that this field, these four fields are inserted at one point, so many terms will have the same structure. And in fact, if you look closer, there are only three types of structures that appear. So one type of structure of contractions appears when axes with the indices are contracted with the axis without the index. So let's consider this contribution first. Okay, so let me draw it as a diagram from the start. So we have external points, x1, x2, x3, and x4. And then, in principle, we have four phi's that corresponds to the interaction of the fields. And since these phi's sit at the same point, it makes sense to draw them as just one dot with four, with four lines going out of it. And now the combinatorial problem is to connect the external points to this vertex in all possible ways. Or, okay, we actually draw the contractions, but at the end, this can be depicted as connecting the lines. And so, well, in how many ways can we do it? So let's start with the x1. So x1 can connect to any four of these lines. So it can connect to any four of the phi's. So if we connect it to one of them, but then there's complete symmetry, right? So the resulting expression will not depend on with which of the phi's it connects. So we connect it with one of them and multiply by 4. So x2 can connect with three external, well, with three in three ways with the internal vertex. Then x3 has two possibilities, and finally there is no freedom for x4. So what we get is 4 factorial terms, but they give one and the same expression. So this 4 factorial actually cancels 4 factorial in the interaction Lagrangian. And the real incentive to introduce this 4 factorial to normalize the coupling by in this way is that in perturbation theory, typically the combinatorics is such as that it cancels the these factors. So this term gives what? It gives minus lambda integral d for x. And then we can read it out from the picture. So here is the interaction point. So what we need to do is we need to assign a propagator to each line, multiply all of them, and here they will appear under the integral. So we'll have an integral of d of x1 minus x, d of x2 minus x, d of x3 minus x, d of x4 minus x. So then we go on to the next type of contributions. And so, well, we can consider the case where, so we classify, yes?
What happened to the lambdas?
Lambda should be here. Should be multiplied by minus a lambda. So what comes next is when we, so you say that this term is distinguished by the fact that we contract phi's to the external lines, to the external points in our Feynman diagram. But we could have also contracted phi with phi. And so let's consider the case where we have one such contraction. So here is our interaction vertex. We contract two of the fields with themselves. And then we can connect the remaining two lines to the external points. And there are several ways to do it. Let's consider the case where they connect to x1 and x2. And then x3 and x4 have to be connected among themselves. So we want to consider diagrams with this topology. So let's see what is the combinatorial factor associated with this diagram. So again, we should have started with x1. We know that x1 has to connect to the middle. So that would give a factor of 4. Then x2 have 3 possibilities. So the combinatorial factor is equal to 4 times 3. But then the other two phi's connect among themselves, and there is no choice anymore. So you see that here cancellation is not perfect. We are left with a factor of 1/2. So the diagram, the analytic expression for this diagram is minus I lambda divided by 2. Then dx3 minus x4 d of 0. So you see that this propagator connects a point to itself, so its argument is 0. And finally, the integral over x d of x1 minus x, d of x2 minus x. So what's the origin of this 2? There is actually a way to understand it if you look at the symmetries of this diagram. So you see that it's completely symmetric under reflections of this bubble. So if you make a symmetry transformation that interchanges these two ends of the propagators, it will be the same diagram. So 2 is the number of symmetries of this diagram.
Sorry,
Yes?
you drew one line for one reflection symmetry and started the other symmetry.
So there are two transformations. One is trivial identity transformation that does nothing. And the second transformation is reflection. So the symmetry, so the symmetry of this diagram has no symmetries.
Or not the identity.
Okay, it has one symmetry, so we divide by 1, the whole expression. Here it has identity plus something else, and in total we have 2 symmetries, and we divide by 2. You had some question?
So the symmetry we're referring to basically swaps the legs of X which are attached to it.
Exactly. So finally, there's a possibility that the legs that that emanate from the interaction vertex connect among themselves. And then, of course, the external lines should connect. Well, so here we should add, this is not the whole story, we should add all possible permutations, right? So we should insert this bubble in between x1 and x4, x2 and x3, etc., etc. So then this diagram, well, it has well, let's count how many. So first, let's count how many combinatorial. So how many weak contractions lead to this topology? And so let's see. So if we start with this line, then it has 4 possibilities. It has, let's say, 3 possibilities to contract with. So we have 3, and so then we choose 1. We have this, say, upper bubble, and then the lower bubble is has no choice. So the combinatorial factor is 3. So the diagram altogether will be divided by 4 factorial divided by 3, I think is 8. And then we'll have d squared of 0, and then integral d for x of 1. So so this 8 can again be associated with symmetries. So, so you can reflect each of the bubbles independently, and then you can swap 2 of them. So this generates a group of the group of degree 4 of degree 8. But then the expression, the analytic expression of this diagram doesn't look nice. It is proportional to the volume of space-time. So better canceled somehow, right? And what happens is that, so in the master formula, we have numerator and denominator. And so this contribution exactly cancels, is canceled by the denominator. Yes.
Do you want me to include outside the integral of the contraction of x1, x2, x4?
Oh, yes. So this multiplies, right? So this multiplies. What it multiplies is actually the Green's function of free fields, right? So what is the end answer? So the end answer is that g of x1, x2, x3, x4 is equal And here we can represent it by just by diagrams. So this will be equal to minus I lambda times this cross diagram. And then plus the free field diagrams, but with dressed propagators. So where for the dressed propagator, we have the following expression. So it's equal to just the propagator, and then minus I lambda divided by 2 times the propagator with the bubble.
Would you say that this sum of diagrams equals the Green's function for the interacting fields? Isn't that just the first order correction?
Oh yes, sorry. So this is, let's say this is J1. Or what? No, I'm sorry. I got confused. This is the full Green's function up to order lambda squared, because these three terms contain the tree-level contribution without corrections.
Tree level?
So tree-level. So you see that. Let me explain. So these three terms contain the Green's function of the free fields, right? So when we take this free part of the propagator, then the zeroth order will be contained in these three terms. Now, so pictorially, if you look at these diagrams, so some of them have closed cycles. So in field theory, those closed cycles are called loops. And the terminology goes as that. So we'll call this diagram a loop diagram. Actually, this would be called a one loop diagram. And this would be called a tree diagram. So because it has a structure of a tree, it doesn't have any closed cycles as a graph. Yes?
How does the two-loop term cancel by?
So what happens is that, okay, so denominator, of course, produces something proportional to the free Green's function. So it gives some, because it's, it's in the numerator you will have, you don't take the exponential, don't expand it, you just expand it in the numerator, where phi of x contracts with itself because there are no other insertions. And then because it stands in the numerator, when you write something like that, right? So lambda times c, this is equal to 1 minus lambda c plus something of order lambda squared. So because of this minus sign, it will compensate for this diagram. Now, with a little bit of work, one can show that these vacuum diagrams, so these diagrams that do not connect to anything on the outside, they're called vacuum diagrams or vacuum graphs. And the vacuum graphs, they cancel by the denominator always. So this is a general statement. And so finally we can formulate Feynman rules. That will be valid to any order of perturbation theory. So, so you see, here, you should be able to see the general structure from this example. So, in general, when we expand further to higher orders, we'll produce more integrations over x. So each integration accompanies phi raised to the fourth power. And so we'll have a vertex with four field lines that come out from it. And then each vertex is associated with a factor of minus lambda integral over x. So x is the position of this vertex in space-time. Then, if you have a propagator going from point x to point y, this is equal to d of x minus y. So if you have a line that goes from x to y, you should assign a propagator to it. The idea is that to compute a Green's function to any given order in lambda, you should draw all possible diagrams. But without vacuum bubbles. Then multiply all propagators in a given diagram and integrate over internal vertices. And then you have to divide by the symmetry factor. Yes?
Yeah, I have several questions. So these are Feynman rules. I would appreciate figuring out what we apply them to. Is this, suppose that we want to calculate the Green's function associated with an interacting field, then we Taylor expand in our Masford formula and have the first order correction. Is it the first order correction to which we apply the Feynman rules?
No. This applies to any order. So the
Okay,
order.
So a correction.
So you see that each vertex comes with a factor of lambda. So if you want to compute correction of order lambda to the 10, you draw all diagrams with 10 vertices and say 4 external points. So once you enumerate all the diagrams, each diagram gives you some analytic expression obtained by multiplying all the stuff that appears inside and integrating.
So I start out with a Green's function for an interacting field. I use the mastered formula, I Taylor extend the mastered formula, I have a correction, and it's to the correction to which I apply the Feynman rules.
The Feynman rules is a shortcut to visualize the correction. So in principle, you don't need anything apart from the master formula and the Wick's theorem. So this is a nice way to visualize it. So instead of expanding each time, you just draw these pictures, right? So you don't think about this formula, draw this picture.
It's just, I'm trying to figure out, suppose that I have a problem and I'm going to apply the Feynman rules. What precisely is the problem, and what is the setup of the problem, and what stage do I apply the Feynman rules?
Okay, so the problem is to compute the Green's function of a field theory for which you have the master formula. And then to compute with this master formula, you need to calculate complicated Green's functions of free fields at the end. So which we do using the Wick theorem. And by the way, if you ever have to do Feynman diagrams, the best way to do it is just to do it, at least at first, you should do it step by step, so starting from the Wick's theorem like we did it here. Okay, and then doing all the contractions. Now with Feynman diagrams, this gives you the answer much quicker, because you see, instead of doing 105 contractions here, we just draw this one, and actually just two diagrams. This diagram and that diagram over there with the bubble, and we know that this is the full answer. Yes?
So I'm not sure why we compare
Why is it useful?
Yeah, why do we?
So far, it's just something that we can easily, well, that we know how to calculate. Now, later we will see that you can express interesting quantities through Green's functions.
So I'm thinking like, so maybe I can ask like, why do you have the 4-point function rather than 2-point function?
This is this is an example. I mean, we could have studied 2-point function, 6-point function. Yes.
Could you maybe like expand out one of those bubble terms? Because I don't really see how it would look like. Because it looks like you would have, like in the second term, that you would have like ones with like 2 bubbles. Or I don't know.
You're talking about this or about this?
Yeah, but like how that works into those the equation above. Like one of the terms.
Okay, very good. Let's just see how we get it from the Feynman rules. So Feynman rules, so suppose that someone gives you this expression. So how to read off the analytic expression? So this is point x1, this is point x2, and the external point is x. So actually, let me do it here so that you see this rule. So first of all, we draw all possible diagrams. So one of the diagrams will be this one. So then we should multiply all propagators. And what propagators we have here? So actually, we should multiply both vertices and propagators. So the vertex give us a factor of minus I lambda, and then integral over d for x. So then we should multiply propagators, and we have 3 of them. So one connects x1 with x, then the other connects x with x, and the third connects x with x2. Then we also realize that this diagram has a symmetry, so we should divide by the number, the order of the symmetry group, which is 2. Yes?
What about the couple diagrams? Couples.
Here they don't appear. You mean diagrams like that? So you see that they appear. They would have appeared if we had a vertex like that in our rules. And so if you look back, this vertex would correspond to the interaction of the form lambda divided by 3 factorial times phi cubed. So in a theory where an interaction Lagrangian contains cubic interactions, we would have had this diagram. But with the quartic vertex, we cannot write it. We cannot draw it. So, any other questions? Yes.
So you mean this, the third argument is the vacuum bubble.
Yes.
So do you mind repeating why it's why it is a fraction?
Because it doesn't connect to anything
So
on the outside.
do you mean that this term turned out to be a constant? So
This term turns out to be a constant that's actually cancelled by the constant in the normalization factor in the denominator of the master formula. Yes?
So once you have this prescription for, okay, so it seems that this prescription involves just the correction, or one of the corrections to the formula for the Green's function for the interacting fields. So, and this doesn't involve any of the blobs that you drew earlier. So where do those come into play? Just when you put together the correction term together with the free field term? And,
You mean this blob?
yeah.
This is so you see with diagrams you can do lots of shortcut notations, okay? So in principle, each of these terms is a sum of 4 terms, because we can insert this bubble here, there, or in both lines. So you see here we have 4 terms plus 4 terms, so there will be 24 diagrams that we can write down. But we can package them into one simple expression if we first compute the correction to the propagator, denoted by blob. And then we have only three. So we do it in 2 steps. We first we find correction to the propagator, and then we use this corrected propagator in here. So that saves a little bit of space. So I guess we should, let's make a short break for 3 minutes.